Okay, hi everyone. Today we're going to solve this problem that is a LeetCode 79 word search, and it's a medium problem, and it has a very decent like to dislike ratio. So yeah, it's a good problem. Let's see. We are given an m cross n grid of characters board and a string word. So we're given two inputs. That is one is a matrix of characters and a string that is word that we need to look for. So if the word exists, if the adjacent elements like this a b c c e d exist in the matrix, the word that is given to us, then we return true, otherwise we return false. The word can be constructed from letters of sequentially adjacent cells. So for example, we have A, then we can go to B or we can go to S, where adjacent cells are horizontally or vertically neighboring, which means that we can go to A, B, or for example, we are at F. Now we can go to B, we can go to C, we can go to D, we can go to S, right? We can go to vertically adjacent or horizontally adjacent, but we cannot traverse to the diagonally adjacent bit, which means that we cannot traverse to this C or this A or this A or this E. So the next condition is the same letter may not be used more than once. So for example, if we have A, then we have B, then we have C, I cannot use this C again. I need to look for the new character in the word and the new coordinate in the matrix which is not been used earlier. So this is the conditions, this is the problem. Let's see how we can. So let's see some test cases in order to understand it better. So we have this board and this is the string a b c c e d. So we are at this character, we are at this, let's say, coordinate, and from there on we say that let's look for the another character, that is b. Do I have b in downward as a down adjacent? No. Do I have b as a left adjacent or a right adjacent? Yes. So I will go to this b. So from this b I need to look for c. Do I have C? Yes, we do have C in this side. So we'll go to this side and then we have C again and so on. Similarly, this example and this example. But let me give you an example where you can understand it better, that this is that what this problem is actually asking from you. Yes. So for example, you have this string, right? And the string is A, B, C, C, um, F, right? So let's say at this part you don't have, or know how to do this. I was trying to be a smartest, but it's not going to work, I think. So regardless, let's say we have this. Uh, so instead of E at this place, we have a character. Instead of E, we have a character, let's say C again, right? And yes. So now we start reversing on this matrix to look for the character, and we see that okay, this is A and this is A. These are matching. This is giving a promising result that I can find a string from this A. So I will say okay, A, and then I will go to another index, that is another cell, that is B. Fine. Then I will go to another cell, that is C. Fine. Because from A you can only reach to this B, otherwise it's an S and we don't need S. So from this B now we need to reach to C, and you have options as F and C. Obviously you're going to choose C because F is not the valid option. And from C now you want to go to another C, but now you have two options. You will say that I will continue with this one, which is a left option, right? So you will go to left side, and this is a DFS tree that I'm forming here, because now I think you can observe that this is a DFS tree, nothing else. So from this C now I want to have F, but I cannot have F, I can have S, and this is not a valid string. So I will backtrack to it and I will say, is there any other neighbor of C? No, we don't have any other neighbor of C. We do have this neighbor, but this is already used, right? and we are marking the characters that we have already used. And then I will say that C is not a valid option because it doesn't have any neighbor, and the neighbors that it does have are not valid characters that we are looking for. So I will say that C is not a valid option, and I will backtrack to the previous C, and now I am at this C. So I made this decision, but I backtrack it, right? Now I will make this decision, and I will say that I will go to the downward direction, and now I find this C, and from this C I will mark it as traversed. And what are the options that I have? So I need to look for F, and this C will give me S, F, and E. Obviously I need F, so I will be on the F side, right? And at F I will say that I have found the last character of the string, which means that I have found the string in the matrix, and I will return true. And from here on, the ultimate value of this recursive call will be true, that the string is found in the matrix, and that's our answer. Now there could be a condition where we haven't found the string. For that we are obviously going to try each and every possible string in the, or a possible answer string in the matrix. But if it doesn't work out, we are just simply going to return false. So I think now you can see that the whole procedure is a DFS, traversal or searching, right? And we need to backtrack in order to correct the decision, or the discard the wrong cell that we have counted as our answer. So this is a backtrack question. Now let's see how we can implement this. So first thing, we're going to traverse all the whole matrix and look for the first element, first character of the word. And if it does matches, then I will say, okay, so from this point I can start my string. So I will say board dot size I plus plus, j is equal to 0, j is less than board 0 dot size, and j plus plus. And at this place I will say if word of let's say 0 is equal to the board I and j, which means we have got the first character in the matrix of the word in the matrix, and from this point I can start my search part. And I will say check word. So for example, so first of all we need to pass some arguments. So first will be the board, right? Then we need to pass the I and j coordinates which we are on currently, and then I need to pass the word string, then I need to pass the word index that is initialized with 0. And if it does came out to be a true, the whole expression is true, that word index and the check is also true, that we have found which means that we have found the string, so I will return true. And let's say we haven't found any string in the matrix, and we looked for them, we searched for them, but we didn't found any string, we didn't found any combination of characters that are satisfying the condition, then we return simply false. Now we have bool, because it's a bool type of check function, and it will have a vector of vector character board, and the current coordinates, that is I and j. Then we have a string and a reference word. So board and word are references. Why? Because we need to reduce the overhead cost. And we have word index, right? So first thing, if word index is equal to word dot size, which means we have looked for all the characters in the word string in the matrix, and we have successfully found them in the matrix, and we'll return true, right? Another thing is, so these are the base conditions, right? So first of all, let me write the base conditions, and then we need, now if there is a illegal coordinate, so for example, if I is less than 0 or j is less than 0 or I is greater than equal to board dot size, or j is greater than or equal to board 0 dot size, so this means that this is an illegal index, and I will simply return false. Now another thing is, if board of I and j is not equal to the word, is not equal to the character that we are looking for, the next character, then I'll say return false, that this cell is not good for our processing. And the last part is, if it's already a visited cell, so I will say that board of I and j is equal to dollar. Dollar means that it's already a visited cell, and I will return false, that from this point we cannot have our answer, and let's return false. Okay, so now we need to find some values, but before that we need to mark that cell in the board as visited. So I will say board of is equal to ij is equal to a dollar sign, which means it's already visited. And now I'm going to traverse in, so that marking as visited cell, and then we have, now we're going to traverse in the down direction. So if check yeah, board, and then down direction it will be I+1 j and word as it is, and word index is going to be obviously the next index, that is word index +1, and if this is true then return true, right? Similarly we are going to have another directions, another 3 directions that are up, and now we have up, after down we have up, then we have left, then we have right. Yes, so for up I will say that I is as it is, and sorry, for down it's I+1, for up it's I-1, for left it's I as it is, and j should be +1, not +1 actually, it's -1, and I as it is and j should be +1 for right. And yeah, now it's the time when we have traverse all the routes from that cell. I will obviously mark it as unvisited because now I'm not dealing with that cell anymore. So I will say word is equal to word index, and after that if we haven't returned true from these conditions, which means the string is not there, and I will return false, right? So I think this is it. Let's run it. Okay, I think it's doing good. Yeah, it's good. So yeah, so this is it. Now you must be thinking, what is the time complexity of this solution? So for example, we are traversing on the whole matrix, right, on the whole grid, every element. So we are very sure that whatever the searching time is, it's multiplied by, in the worst case it's multiplied by m cross n. Why though? Because we are traversing all the elements, we are checking for all the elements, and in the worst case there could be a case where we have, let's say, a string a b c d e, and we do find a b c d in every part of the matrix, in at every cell, let's say an average cell, average case, like half the cells we do find a b c d, but we don't find e, which means that, and let's say for this is a cell, and you can go in this direction, you can go in this direction, you can go in this direction, right? Now you must say that you can also go in this direction, but not, you cannot, because there will be one direction from where you are coming. So let's say you are coming from this node, then you won't go back to this node, you won't go back to this cell, right? So you only have 3 directions to go on. So it will be, now you have 3 options, so that means 3 raised to the power l, because l is the length of the string, word, and 3 is the options that we have, because we cannot go back to the string, go back to the cell where we are coming, where we coming from, right? So that is why we only have 3 options for the new cell, and that is 3 raised to the power l. So this is the big O of m cross n, 3 raised to the power l time complexity. I think this is the main reason why the constraints are so low, because only then it's going to work out. Yeah, it's like m cross n, and this is m cross n, this is like 36 into 3 raised to the power l, so 3 raised to the power of 15. I don't know, whatever it is, but it's a huge value, let's just say. It's a big value. Why don't we search it? So 3 raised to the power of 15. Yeah, it's a pretty big value, and multiplied by 36. So 4, 6, 8. So that's like 5 into 1 2 3 4 5 6 7 8. 5 into 10 power 8. Yeah, that's a very big problem. I think the time would be around 1.5 second or 2 second, whatever it is. But yeah, this was the problem. This is the time complexity. This is the solution, a backtracking DFS solution. So yeah, that's it. Thanks for watching, guys.